Hi everyone. So in this video I want to continue with discussing the different types of hybrid orbitals that you can make out of different atoms depending on the molecules that we're talking about. Previously we talked about the sp3 hybrid orbitals and the example molecule there is CH4 methane, and then we also talked about in the previous video the sp hybrid orbital which I used the BeCl2 molecule as an example. Now I want to talk about the sp2 hybrid orbitals, and I'm going to use the Bf3 molecule as an example. So I hope that at this point you will be able to draw a Lewis structure for Bf3 is fairly straightforward. Boron again is one of the atoms that can violate the octet rule, in this case being only having 6 electrons around it, and that this molecule exists and it has a trigonal planar structure. The angle between the FBF atoms is 120 degrees, and what we want to do again is to show that the hybrid orbital is the only way we can explain why this molecule exists. And so to do that we need to look at the electron configuration of boron, which is shown in orange here. And boron has 5 electrons, so the valence shell would contain 2s2 and 2p1, and as you can see it only has one single electron, so that's not going to explain the 3 bonds that boron makes. So in order to do that we need to promote one of these electrons from 2s to 2p, which results in 3 single electrons, and then of course we have to make all those electrons the same type, and so to do that we hybridize all these 3 orbitals, and because you have 2 p orbitals combined with 1 s orbital, the name becomes sp2, and since you have 3 orbitals to start, you also have 3 orbitals to end, and so you have 3 sp2 orbitals that is now part of boron instead of using the standard orbitals. So then what you do is then you illustrate boron, which is shown in the middle here with the brown or the brownish color orbitals, which is the sp2 orbitals. And again, you can rationalize why this would be 120 degrees, and it's a little complicated maybe to see it just from shapes, but remember that basically what we're doing here is we're adding two p orbitals which are 90 degrees from each other, and then you have s orbitals. And again, the addition, it depends on whether you're adding positive or negative phases, because that's what p orbitals have. So you want to be a little careful there. But overall, what you get is basically a triangle shape here. And of course, a triangle shape, then that means there's 120 degrees between each sp2 orbitals. To illustrate the bonding then in Bf3, what I need to do is just overlap that with the regular atomic orbitals, standard atomic orbitals from F, which would be a 2p orbitals, because that's where the single electron in fluorine is located. And so that's what you get here. You get this picture as your illustration of your Bf3 molecule, which is there are 3 sigma bonds, right? And it's an overlap between the p orbital and the sp2 orbital, okay? And it's trigonal planar structure. Now again, I want to point out this, in the promotion, the mixing, we only use 2 of the 2p orbitals, and 1 of the p orbitals is not used, so that remains available later on to make to host additional electrons. And you'll see that when we have multiple bonds, that's where that extra electron is going to go to. Okay, so we talked about sp3 orbitals before. In fact, that's how we started the whole discussion on hybrid orbitals. So I'm going to skip that now and talk about the next hybrid orbital, which is the dsp3 or the sp3d, depending on which textbook you consult. So this is the example for this molecule, for this hybrid orbital is PCl5. So I'm putting the Lewis structure of PCl5 here as a reference for you, but again, I fully expect you to be able to draw this at this point. Again, phosphorus is something that can violate the octet rule because it's on the 3rd period, and just the same way as we've been talking about the previous one, it's not, you can't imagine that this molecule will exist just by using standard atomic orbitals, because there's only 3 single electrons. But if you were to promote this not to the p orbital but to the d orbital, right? Because if you were to promote it to the p, then you're still going to be left only with 3 electrons. So you have to promote this in such a way that you actually get all the bonds that you observe in the molecule. In this case we have 5 bonds, so we need 5 single electrons. So we took this s orbital electrons and promoted all the way up to the d, the 3d orbital, And now we have S, 1 electron in S, 3 electron in P, and then 1 electron in D. And then what we do is then we do a linear combination of all these 5 orbitals together to form 5 sp3d orbitals. You see the name makes a lot of sense because you're combining 1s, 3 p orbitals, and 1 d orbital to make this sp3d orbitals. And wouldn't you know it, when you actually form this sp3d orbitals, you notice that the lowest energy structure that's made out of by these 5 orbitals is the trigonal bipyramidal structure. So as a result, when we illustrate the bonding of PCl5, we note that each one of them is an overlap between an sp3d orbital with a 3p orbital from chlorine, and there's 5 of these overlaps, so there's 5 sigma bonds. And the structure is trigonal bipyramidal, and you have the bond angles associated with trigonal bipyramidal structure. And the next molecule I want to talk about is the last illustration of a hybrid orbital, which is SF6. Okay, so again, I want to provide the Lewis structure of FS6 here just as an illustration so that you know that SF6 has, of course, 6 bonds here, another atom that can violate the octet rule. This is a octahedral structure, as you know from Vesper. And again, you know, if we want to illustrate this bonding using valence bond theory, you're not able to do that if you're just using the standard sulfur atom, but you have to make 2 promotions in this case in order to get 6 electrons that are single for the sulfur atom to be able to make 6 bonds. So I'm going to promote one of my electrons from the s orbital to the d. I'm going to take one of these p orbital electron and promote it to the second d orbital, and so then I have 6 electrons total. I'm going to do a linear combination on all these 6 electrons all together, 6 orbitals together, to form my s p3 d2 orbital. And so I have 6 of these guys, and again their energy is located, as you can see here. This is the 3d orbital, this is the 3p orbital. Their energy is slightly higher than the 3p because it has all the p, it has 2 d's, it has 1 s, and the s brought the energy down, but then the d brought the energy up, so it's a little bit higher than the 3p orbitals. And then of course upon bonding, the energy would actually decrease. Okay, so then to illustrate the bonding in SF6, then I would imagine, you know, I would draw something like this, where the SF6, the S atom itself has 6 of these lobes pointing out for the sp3d2 orbitals. And of course, again, this matches up with the Vesper prediction because this structure is actually an octahedral structure, the structure of the sp3d2 orbitals. And so the overlap, as you can see, is between the sp3d2 orbital with the 2p orbital from the F. So that's how I would illustrate the bonding. That would lead us to have 6 sigma bonds, right, because of these 6 overlaps that are all cylindrically symmetric around the bond axis. And the structure would be octahedral based off the fact that the D2sp3 orbitals are octahedral. Okay. All right. So now what I want to do is summarize all the different hybrid orbitals we talked about. We have the linear hybrid orbital, which is the sp orbital, and that there's 2 of them, right, being formed together. That's a linear combination of 1s and 1p orbital. Trigonal planar would be like this, triangle shape. That's sp2 orbitals. There's 3 of them. And this is obtained by doing a linear combination on a 1s orbital and 2 p orbitals. And then a tetrahedral one which is the 4 sp3 orbitals, you would get by making a linear combination of 1 s orbital and 3 p orbitals. And then the trigonal bipyramidal you're going to get by making a linear combination of 1 s orbital, 3 p orbitals, 1 d orbitals to get 5 sp3d. Or DSP3, there's different ways of naming this. And then octahedral, you're going to get 6 sp3d2 because you're combining 1s, 3p, and 2d orbitals, resulting in an octahedral shape. One thing I want to point out is that, you know, in reality, if you were to try to use the valence bond model to predict the structure of molecule, what you have to do is really make calculations for each of these overlap that you got right, between the hybrid orbital and the standard atomic orbital, and try to calculate which one has the lowest energy. And that would be the structure that you would pick to represent the experimental structure. In our case, of course, we don't have the ability to calculate the actual energy of each of these overlaps, right? The overlap between, say, the overlap between, one of these sp3d2 with the f orbital, for example. So we wouldn't be able to know which hybrid orbital to use by doing calculation, but what we can do is remember that the Lewis structure can serve as a guide for us, because all of you know how to draw Lewis structures, so all of you can predict actually what kind of electron geometry a particular molecule will have. Like in this case, there will be an octahedral electron geometry. And as it turns out, if you're actually making the calculation, right, it turns out that the lowest energy structure corresponds to those electron geometry that was listed in VSEPR. So in other words, if you know VSEPR, you can basically predict what hybrid orbital you're going to be using. So if you have a electron geometry that's octahedral, automatically that would imply that the hybrid orbital that's going to be used would be a D2sp3 hybrid orbital. Okay, so to summarize that part of it, I want to mention that this is really the way we're going to use the concept of hybrid orbital in this class. You're going to start by working with the molecular formula that's given to you. So for example, I might give you something like C2H6, for example. And then what you have to do is then think about drawing a Lewis structure for that molecule. So you would draw your C2H6 as a Lewis structure. And then for each of the central atom, you would then think about what is the electron geometry or electron group arrangement. Okay, so if it's, figure it out for each central atom. Is it linear? Is it trigonal planar? Is it tetrahedral? Is it trigonal bipyramidal? Or is it octahedral? Once you have that, then what you need to do is then assign the appropriate hybrid orbital for each of those central atoms. In other words, so if you have, again, for example, if you have, a linear shape, then you would assign an sp orbital for that central atom. If you have a trigonal bipyramidal shape, you would assign sp3d hybrid orbital for that central atom. So that's the way we're going to apply this in terms of practice. Okay, in the next video I'll show you an example on how to actually do this.